Okay, so this is the second 5.4 video. I don't know if I'll make the quote-unquote net change theorem into a separate third video, or this will just be the whole second half of 5.4. 5.4 is very important. Okay, I think in my notes, I essentially give instructions on how to read and vaguely interpret, because the mean value theorem for integrals and the average value of a function, those are pages 321 and 322 in your book. Again, please get your textbook out, and I'm going to very briefly talk and give a summary of 321 and 322. Just because I don't know, maybe me saying things verbally is helpful. I don't know. I guess that's kind of what they pay me for. Oh, hold on. What did this thing do? Okay, sorry. Hearing like a beeping sound. Hopefully everything's still recording okay. I really don't want to re-record these videos. So average value of a function. Okay, so the mean value theorem for integrals. Hold on, I'm just gonna double check this real quick and just make sure. Okay, good, my microphone's still working. I don't want to be talking to nobody. Mean value theorem for integrals. Page 321. To be honest, not really important. The mean value theorem for, like the normal mean value theorem, super important. If you remember that is mean value theorem is tied closely to Rolle's. Well, Rolle's is a subset of mean value theorem. That's the whole, like, if a function's basically continuous and differentiable on an interval, the slope of the secant line between the endpoints is going to be present as the slope of a tangent line at least at one point on that interval. That's the normal mean value theorem. This mean value theorem for integrals, in my experience, it's not really referred to. If you look at the blue box top of 321, imagine yourself dividing both sides of that equation by b minus a. Okay, so if you divide both sides of the equation by b minus a, then you would get f of c equals that integral thing divided by b minus a. Boom, now flip over to 322. Boom, it's not exactly written like that. It doesn't say f of c, but it's written as 1 over b minus a, which is the same thing as dividing the integral by b minus a, times that integral. And what is that? That's very important. So 322 is very important. That is the average value of the function f on the interval a to b. Also notice common mistake in understanding, that is the integral of f. You would not like integrate f prime or something here. No. So what that's saying, again, I think I have this written out in my like long thing of notes, and I think I told the sub to print it out, and hopefully she gave it to you, and hopefully you actually have it and didn't lose it. It's, I think, online somewhere. I don't know. Ask the sub. What that's essentially doing is it's kind of like adding up, like if you're averaging 5 numbers, right? If you have like 5 test scores and you're averaging it out, you would add up all 5 of the test scores, divide by 5 because you got 5 test scores. That's your average. So pretty much the same thing here, just in calculus form, right? Integral is a type of summation. It's like you're summing up all those like infinitely many f values, right? Again, to find the average of 5 test scores, you would just add up the test scores themselves. You wouldn't need to add up derivatives of the test scores or weird other things. No, you just add up the test scores directly. Same thing here. You're integrating the f values directly. If you're wanting to find the average value of f, you're adding up like infinite number of f values directly, between a and b. So it's like the area under the f curve from a to b. And then you're dividing by kind of like, quote unquote, how many x values you have. So you're dividing by the difference between your two endpoints, right? Your two bounds, your difference between B and A. Okay, that idea is pretty basic, but it's super important. They will throw that out at you at any time on the AP. It should be a pretty easy idea. Again, if you just remember it as you're literally averaging a function, you're adding up the function values on the interval, dividing by essentially the width of that interval. That idea should be easy to remember. So don't forget it. Don't misuse it. Don't think there's some weird derivative thing in there. It's easier than you think it is. So you can see the example yourself. It is what it is. Again, the mean value theorem for integrals thing, page 321. I don't even have that in my mind. Pretty much can just forget it. The example on 323, that's way overly tedious. Don't look at that. Okay, so second FTC. That's the main thing that you're here for today, folks, is this second FTC. Again, technically, if you start Googling online, they may switch what they call the first and the second FTC. It should be pretty obvious which FTC they're talking about. So the book calls it the second FTC. We'll call it the second FTC. Sometimes, I don't know, in my old materials, sometimes I refer to it as like the difficult FTC. Okay. It's the more kind of like heady FTC. The first thing that we need to think about before we just officially just spit out this. Sorry, I don't know if this being closer or farther away is better. Before I just spit out this formula for the second FTC for you, and you just blindly follow it, I want to take time to talk about what's this whole idea of like an accumulation function. Yeah. And this is probably, this is a very kind of strange concept. So before we get too far into the second FTC, I'm actually going to have you turn over in your book, hopefully you have your book, to number 84 on page 331. So let's say this is the intro to the second FTC, and we're talking about accumulation functions. Accumulation function. Okay. 84, so this is page 331, number 84. We're going to use this to introduce the second FTC. It goes along with it. It has a graph. Well, I guess I have to draw this graph. I guess if I was smart, I would have all this pre-drawn, so I wouldn't have to waste time, but I guess you guys have to draw on your own paper, so like that. And then hit 0 at 4, we'll call that 4. We'll call that 4 up there. Call this -4 down there. 2. This hits a -4. And we have just a little V-shaped thingy. And then 5, 4 is a point. 5, 4 is a point. And 7, 4 is a point. 7, 4. Not too bad. 8. Okay, not so bad. That is the figure that we use for this thing. Okay. This is saying let g of x. So this function here, this is very important. This function is a graph of f of x. Super important. F of x. This is not g of x. So let g of x equal. Here's the kicker. All right. It's an integral. Bottom bound is 0. we're taking, coming back to the top bound in a second, we're taking the integral of f of x dx. All right, so far so good. Here's the kicker. Oh, that hurts. Oh, that top bound is an x. Oh, we have a variable in our bound. Actually, you know what? I do this every time. Okay. Let me explain. Technically, and this is kind of right, but you can't really have this x, the upper bound be x, and there be an x and an x. I almost can't explain too much as to why this now can't be x and that can't be x, or else it would make your brain hurt and it would make my brain hurt, and it wouldn't be a very useful explanation. This, since the upper bound is x and it is an x, and this, right, this graph over here, this is the x and this is, the y. So the graph is in terms of x, and that matches this upper bound of x, so that matches this. Kind of because of that, they don't write, so they're going to write a t here. Let me just cut to the chase. They're going to write a t here and they're going to write a t there. It doesn't have to mean time. They just have to choose a different variable, because technically you're taking a derivative of f with the input variable can't be x, and then you also have an upper bound x, because you're actually plugging in x as your upper bound, and that x can't anyways. And then this has to match this, so if those both have to be the same, it doesn't have to mean time. They essentially just had to choose another dummy variable to use as the input here and here that's not the same as your upper bound, and your upper bound is going to be x because this thing is x on the graph. I know it's kind of confusing. It just is what it is. And I forget every year. I just go into automatic mode and start writing X's, but then I have to stop myself. So when we do the second FTC, you'll see it, again, that's why that makes the second FTC seem so confusing, that you see these T's and you're like, what in the world? And where did time come into place? And why the T's and the X's? Don't think too much about it. But yes, you do need to write. Just go for T's because that's what's traditionally used. Technically, it doesn't have to be in time. Okay, hopefully that's sufficient to at least help you know that you need to write T's, but you don't have to 1000% understand all that. Okay, so you notice in the textbook, they do have T's there, where I just wrote T's. All right. So this is super weird. I also, I feel like I have to get up on, well, not my soapbox, but I have to play my tiny violin, like they talk about you being, having your sob story and playing your violin, and it's like, oh, who cares? But when I was in calculus, this is where I always tell my students every year. I kind of feel a little bit bad for my own calculus teacher from, oof, it's pretty much half my life ago that I was in calculus. Wow. Okay, I'm old. Um, but so I did not learn myself when I was a senior in high school this whole idea of there being a variable in the bound and a bound of an integral. I never saw that. Never was taught that in class. And then I got to the AP test and I thought, oh yeah, like I got this. Like, I was a good student. I was, okay, whatever. I won't toot my own horn too much, but let's just suffice it to say, in calculus, I had been looking forward to since 8th grade. Like, it was like my jam. And I got to the exam and I was like, oh, easiest 5 ever. I'm going to rock this thing. And literally, I saw these x's in the bounds of these integrals, and I was like, what in the world is this? And I literally just remember that feeling of panic as I was sitting in the room taking my AP calculus test, being like, I've never seen a variable in the bounds of an integral. What are they saying? So like, anyways, this is kind of my soapbox moment that, and I always tell people that, yeah, I only got a 4 on the AP calculus test, but that's in large part, number one, because there were like huge sections like this. The whole second FTC, or the idea of an accumulation function, was never taught to me. Never, never. I promise you. Um, we also did no practice AP questions ever at any time of the year, not even sprinkled throughout the year. And we had no time to review for the AP at the end. I had no idea like what I was going to expect on the AP test. Anyways, so I guess not part of my life's purpose, but I don't know, kind of, I hope that I am rectifying the mistakes of my own calculus teacher so you all can get 5s and rock this test, or at the very least you can go into the test and be like, yeah, I know, we covered that. I forgot it. It is what it is. At least you don't have an excuse to blame your teacher. Anyways, all right, I just always throw that out there. So this is weird, right? G of x equals the integral from 0 to x of f of t dt. What in the world? All right, let's keep going. Part A. I think this, oh no, it's in class, okay. Part A says estimate g of 0, g of 2, g of 4, g of 6, g of 8. That's kind of a lot of, whatever. This is estimate too. You could figure those out exactly. Find. I'm just gonna say find because why estimate when you can find them exactly? G of 0. And this is important. This is not just an intro. I mean, it is an intro as well, but I have to zoom out a little bit. They actually ask you questions exactly like this on the AP tests. So this is actually a really good question, not just as serving as an introduction to the like formal second FTC. They will literally ask you a question like this. Now they won't have you plug in 5 values. This is kind of to prove a point, but they will have you plug in like one of these values. Okay, G of 0 again. This is not F of 0. Okay, so just like I told you back in the fall, that the function they're going to give you is really never going to be the original function. It's usually going to be the derivative, and you got to like kind of like bend your mind, because if they're asking you like where is f increasing, it's not going to be as simple as just looking at the graph and being like, oh, where's the y value increasing? Yay, I'm a genius. Well, here it actually is f of x that they give you, but then they're asking for values of g, and g is found by, this thing over here. So when you're plugging in values of x, it's not that you're just like, oh, plugging in values on like the graph over here and doing stuff like that, and finding y values. No, you're plugging in. So like this g of 0 means that 0 is going in for here, that x, which means it goes in here for that x, which means it becomes the upper bound of an integral. Okay, so, oh, hello. Okay. So g of 0 actually means you're doing the integral from 0 to 0 of f of t dt. And again, it doesn't matter that it's t. It means the same thing. It could be f of smiley face, d smiley face, right? The important thing is that it's the f, right? Well, the integral from 0 to 0 of anything, or the integral from 3 to 3 of anything, if the top and bottom bounds match, it's always going to be 0. It literally doesn't even matter that this thing over here starts at 0. That literally even has nothing to do with it. That's going to be 0, right? Okay, this next one, I'm going to try to zoom in a little bit. Okay, this next one, integral from 0, again, so we're plugging this 2 in. This 2 in gets plugged in here and gets plugged in here. So this top thing becomes a 2. F of t dt, which this just means the area under f from 0 to 2. So what is the area under the f function from 0 to 2? Well, this area right here. That area. Okay. So that's a triangle. So it's, 1/2 base times height, 1/2 times 2 times 4, but it's all negative. Be very careful when you're looking at areas. They can be negative. The AP will definitely love to, well, if you think they're evil, they will love to trip you up, I guess. So what is that area? It's negative 1/2 times 2 times 4. So negative half of 8, so negative 4. Okay. G of 4. Let's zoom in. Okay, G of 4. Okay, now we're going to 4 f of t dt. So 0 to 4. So now we have not just the area from 0 to 2, now we have the area all the way to 4. Okay, hopefully you're kind of now realizing why we call this an accumulation function. Accumulation function. You're starting at x equals 0, and because that's this bottom here says we're starting at x equals 0, right? All these times here, that's x equals 0, 0, 0, 0. We're starting at x equals 0, which that can be some other number. It could be like -2 or 7 or something. But in this case, we're starting at 0, and we're accumulating area underneath this function f. Right, and the accumulated area is equal to, the accumulated area under f starting at x equals 0 is equal to g. Yeah, just let that sink in. That's kind of strange. So that's this area all the way from 0 to 4. So again, it's just like a giant triangle actually, which is, and it's in the negative region. So this is just going to be equal to negative 1/2 times 4 times 4. In fact, you could even think of it as the area from G of 2 plus the area, the extra area accumulated between x equals 2 and 4, but it doesn't really matter. So that's half of 16, 8, -8. Okay, get that. And then G of 6. Let's zoom in. Ooh, too much. 0 to 6, f of t dt. All right, now to 6. 6 is up here. So now we have, should I choose this? Well, whatever. Red's usually negative, but I'm going to use red up here. All right, there's 6. Pretend. And then we're going to have, right, we're going to have a triangle and a rectangle. And this is a positive area. And it's all the way accumulated all the way back from 0. So we're actually, at this point, it would be useful to just say, okay, let's take the area that was accumulated between, in fact, I can even color code it, be fancy. Say, okay, we got a -8 from that negative triangle. And then we have a little trapezoid between 4 and 6, or you can do a triangle plus a rectangle, whatever, doesn't matter. Triangle between 4 and 5 would be 1 times height is 4. Half of 1 times 4. So plus half of 1 times 4 plus this extra rectangle, which is a 1 by 4 rectangle, plus a 1 by 4 rectangle. So we got -8 plus 2 plus 4, so plus 6. So still -2 overall. -2. Okay, get that. And then G of 8, we go all the way. So then we, yep, okay. So then we have to do this whole thing. So then we have more rectangle, more triangle, right? So g of 8, 0 to 8, f of t dt. All right, so now we have essentially, so again, we still have that -8, and then we have this giant, all right, I mean, it's essentially double what we had from the red before, if you want to think that way, like whatever, however you want to do it. So essentially plus, all right, twice of what we already got, plus, so this was a 6, twice of a 6, not that, twice 6, hopefully you can follow that, right, because this thing is like, right, this was like halfway, and so we already did this half, and now we want to add in that half. Okay, I think you get that. Oh, come on. Okay. So 12 minus 8 is 4. Hey, we're back into the positive. Okay. So again, hopefully this kind of gives you an idea. We went kind of like x value by x value, and obviously there's an infinite number of inputs you could have put in there, right? We were literally accumulating area. So like here we started out with no area at x equals 0 because that's where the lower bound of our x was. And we accumulated more and more and more negative area. And then we were still, even when the function f is increasing, it was still below 0. So we had this negative area, and we were still accumulating more negative area. So it was still making the final area more negative. Even up through here, we're adding in additional negative area. So still the value of g was decreasing, which we see here, right? Went from 0 to -4 to -8. Even though f in between x equals 2 and x equals 4, even though f up here was increasing, g itself was still decreasing because we were adding more negative area. We're about to talk about that relationship in a second. This is just a really good question to like conceptually get your head around the idea of accumulation function and yeah, other things. The AP questions love this kind of reasoning in number 84. That's why we're spending so long on it. And then we started accumulating some positive area, right? And then, so our total area was still negative, but it was like less negative. So it's like saying G was increasing, right? So like at G of 6, right? That was higher than G of 4 because we had added this much positive area. And even then we kept adding positive area, right? And even when whether f was increasing or whether f was decreasing, and this gets into second derivatives and stuff, and we will get into the full implications of all this later, but if f was increasing, sure, you're like increasing at like a super increasing rate because you're adding not just more positive area, but more and more positive area, kind of. But even when we were over here, like say when x was in between 7 and 8, we're still adding more positive area, even though we're adding like the additional amount you're adding was less. It was still increasing the total amount, right? So like here, say we were adding, like 2 loaves of bread a day more, and then like the next day we only added 1 loaf of bread and then like half a loaf of bread or something, but you're still increasing the total number of loaves of bread you have. It was just increasing it in a decreasing manner. Again, you can, hopefully the wheels are turning, connecting this to like second derivative type stuff. All right, you can see where all these different levels of derivatives and integrals are gonna all be tying together. So that finally in the end, the amount of positive area that you had was greater than the amount of negative area you had, and so the g function became positive. Okay, so that was A. B, find the largest open interval on which g is increasing. I'm not going to write this down. you guys can follow along the textbook. The largest open interval on which G is increasing. And then find the largest open interval on which G is decreasing. All right, so B, G is increasing on the interval, what? And they say to use an open interval, so we know it's going to be like that. Boom. Just got to know, okay, well, where does it start increasing and where does it stop increasing? And again, this is where I would love to have you guys in person, and then you could like make guesses at it, and then I could kind of, give you breadcrumbs and I don't know, wield the carrot and the stick. I don't know. You know what I mean? I could kind of tell you why your reasoning is on the right track or not on the right track or whatever. But again, it's easy to confuse F with G. F itself, sure, is increasing on the interval 2 to 5. But that has nothing to do with when G is increasing. Okay? And again, they're really just never going to ask you a question that's just that obvious where you just look at a graph and say, well, where is that graph that you see increasing? That's pretty much never going to be a thing. So on what interval is G, which is the accumulation interval, the accumulation integral, or accumulation function of F, right? Because G is equal to, well, let's do this. G is equal to the accumulation function, like F accumulating, starting at 0. So like we said, G, so this accumulation function, where you're taking the integral of F from 0 to x, G's value starts at 0, is decreasing here because you're adding more negative. You know what? It's still decreasing even here, right? Because if say you started out with $100, I steal $1, $2, $3, $4, $5, $4, $3. If I'm still stealing money from you, I don't care if I'm stealing a penny from you. The amount of money you have is still decreasing, right? It could just be decreasing at a decreasing rate, decreasing at an increasing rate, that kind of deal. But it's still decreasing. If I take any money from you, if I am accumulating more negative area, the function that is the accumulation of that area is still decreasing. So G begins increasing when F becomes positive, right? Because if we're now adding, once X hits 4, now exactly at 4, we're adding nor subtracting anything, but just to the right of 4, now I'm starting to add stuff. Now I give you a penny. Now I give you 50 cents. Now I give you $1. Now I give you $5, $5, 5 more dollars, 5 more dollars, $4, $3, $2, $1, 50 cents, nothing, right? As long as I'm giving you money, your total money is increasing. Okay, so hopefully you can see G is increasing on the open interval between 4 and 8. We don't include 4 and 8 because right there, right, you're accumulating no extra positive nor negative area. So G is increasing on the interval 4 to 8. Okay. And G is decreasing. Now, you know what? I'm going to go a step further. They didn't ask this, but let's pretend like we're on an AP question, because they're not just going to ask where the G is increasing. They're going to ask why, or explain, justify, something like that. Sorry. So G is increasing on the interval 4 to 8 because, again, this is where we would hopefully have some kind of meaningful conversation, and maybe you would tell me the right answer, maybe you would tell me the wrong answer, but us talking about it would be beneficial, but okay, whatever. She's increasing the interval because F is positive there, right? We saw that F is positive. That means you're accumulating positive area there, right? I'm giving you money there. I'm not subtracting money there. Right, G is increasing in the interval 4 to 8 because F is positive there. Positive. there or whatever on that interval, you know what I mean? Okay. Woo. And G is decreasing on the interval. Well, if you could answer the first one, you can pretty much answer that one. From 0 to 4, because on x equals 0 to x equals 4, you're right, someone's taking money from you, right? You're accumulating negative area. Even if you're accumulating less and less negative area, right? Even if I take $3 and I'll take $2 and I'll take $1, I'm still taking money from you. Your total pot's going down. Okay. Decreasing on the open interval, woo, that's weird. 0 to 4. Again, not including 0 and 4 because f is 0 there. Because f is negative on that interval, right? Because f is negative on that interval. All right, you get the idea. Okay, we look at that question. Okay, C, identify any extrema of G. All right, well, once we answered part B, you should be able to answer part C. Now, notice this is in like opposite order because from 0 to 4 is down here. So 0 to 4, G is decreasing, and then G changes from decreasing to increasing. And what happens when a function changes from decreasing to increasing? Now, this is obviously not at all what G looks like, but right, if any function changes from decreasing to increasing, we have a relative minimum there. All right, so any extrema of G, well, there's a relative minimum on G of x at x equals 4. Well, because G, where was that? G changes from changes from decreasing to increasing there. Decreasing again because f is, we kind of explained this in the previous part, but I'm just kind of making sure to cover all of our bases. G changes from decreasing to increasing. The reason we know G changes from decreasing to increasing, again, I'm just going to reason directly from the graph we were given. G is decreasing where f is negative, to increasing because f is positive. There. Okay. The next thing, part D, says to sketch a rough graph of G. I'm going to just save that for later on in history. Later on in history. Later on in, yeah, it's kind of the same idea. Well, you haven't learned the second derivative. I mean, you haven't learned the second FTC. Once you learn that, then you would literally just use the same method that we've used from like knowing the derivative of a function and sketching the original. But we haven't directly learned the second FTC yet, so we're going to just truck on with our main objective, which is to learn the second FTC. All right, so let's come down here, and now we're going to, for real, learn the second FTC. Come on. Let's go, people. Go back to when it zooms out, the color gets weird. All right. Okay. These videos just are always so much longer than I expect them to be, but I'm just gonna teach them how I think I would teach them if I was there, and it is what it is. So again, obviously you can stop these videos and start them however you need to accommodate class lengths and days and all that stuff. I'll just be sitting here just trucking along on these videos. Okay. Now look at your book and okay, we're just gonna glance at one more example and then we're gonna like boom, hit you with the second FTC. Take a look at example 6 on page 324. This is page 324. They say, yeah, I don't, they do this for a reason, but, whatever. Okay, it's fine. They go ahead and use this capital F to mean this, which it's no coincidence they're using capital F, which means like antiderivative, which is kind of as an antiderivative. Accumulation, again, this is where you can kind of dive deep and your head can start spinning. We don't have to dive too deep, but notice again the t's. Again, these are just dummy variables. Dummy variables. Right? It doesn't have to mean time. Necessarily mean time. Okay. They give us that function, which they already are kind of like not so much disguising it as an antiderivative already. They say evaluate the function at those values. I'm not going to focus on that necessarily. I'm going to focus on this point. I'm going to focus on what if our goal, because kind of the goal of this example and how they use it is actually to do pretty much what we did in example 84, where we plug in values and we kind of notice like, oh, this is like an accumulation. So if you look at the pictures below in example 6, like f of 0, like they start at 0, and then f of pi over 6 is 1/2 because you like accumulate that much area, between 0 and pi over 6. And then f of pi over 4 is root 2 over 2 because that's the area accumulated under that cosine function between 0 and pi over 4, and so on and so forth. And notice the y values keep increasing because the cosine function is positive there, so on that interval. So you're accumulating positive area each time, and so that the accumulated area is increasing. But I'm going to take this a step closer to the edge to the second FTC. Ish. So this is like kinda. So I'm not exactly following their rules. Like what if we wanted to find the derivative of this thing? Spoiler is what's leading up to the second FTC. If we wanted to find the derivative of this thing. So instead of going by their rules and their objective, I'm going to find the derivative. Well, it's fine. I'll just go straight to the, just use this. Find the derivative of this thing. Okay, there's 2 ways you can do this. Let's look at it this way. Before we find the derivative, let's just take this and just rewrite this. Okay, f of x, this capital F of x, it doesn't really matter right now that it's called capital F of x. Again, technically f of x, it being a capital, does not tell you to do something to the function. It's usually just a label for a function that tends to be used as a label of an antiderivative. Okay, so I'm just going to play dumb and say, okay, I want the integral of cosine evaluated at between 0 and x. I'm just going to rewrite that. I'm ignoring the whole goal of finding the derivative for now. We're just going to rewrite this as an antiderivative thingy. Okay, so the antiderivative of cosine, hopefully you would say, is sine, right? Because that's like the opposite rule of, right, the derivative of sine is cosine, so the antiderivative of cosine is sine. Okay, so I'm going to say sine, and sure, I'm going to just keep using t, evaluated from 0 to x. Okay, again, I haven't taken the derivative yet. This is just rewriting this function thing. That's the integral. Okay, antiderivative of cosine is sine. Okay, evaluated between 0 and x, so that means this is going to be equal to sine of x minus sine 0. Okay, now sine 0 happens to be 0, but it didn't have to be like this. This is maybe not a bad example, but it didn't have to be sine of 0. Like, we could have done the same thing if the lower bound was like pi over 4, and sine of pi over 4 was not 0 at all. Okay, so it doesn't have to work out that you're actually subtracting 0 there. I'm just going to keep it like that. Now, if we're actually finding, maybe I'll start color coding this. Okay, so find this thing. So now I'm going to come down here and write this in green. So f prime is the derivative of this thing. So I'm going to say is the same as the derivative, I'm going to use that symbol, of this stuff. Sine x minus sine 0. And again, that sine 0 doesn't have to be 0. I'm leaving it as sine 0 just to show you that even if it wasn't a 0, it doesn't matter. Okay, so that means you take the derivative of both of these terms, right? So the derivative of sine x is cosine x. And notice, again, maybe this is subtle, maybe I kind of skipped ahead a little bit too fast. Notice, when I evaluated this as an upper bound, that means I plugged in this x where t was, so that this became sine of x. That's why it doesn't matter. That's why I call this a dummy variable, this t thing, because no matter what t is, the upper bound is going to get placed in there. And so, you know, that's why I said it could be cosine smiley face, d smiley face, right? Doesn't matter. You're going to end up plugging in whatever your upper bound is, which that is going to be in terms of x. Boom, gets plugged in. And then obviously this 0 gets plugged in here, you know. Okay, so that's why I have a sine x here and not a sine t. All right, so notice this is sine x, not sine t, because it's already gotten plugged in as the upper bound was an x. Okay, so d dx of sine x is cosine x, and then minus d dx, I'm just going to write it like this, again, just to prove a point, sine of 0. Now, yes, this is 0, but no matter what this would have been a constant. So I could have chosen any lower bound here. This is a constant because this is a constant. This is a constant, right? Now 0 obviously, well, okay, again, that's why this is kind of a lame example. 0 is actually the same constant as sine of 0. That's just a coincidence. This 0, the lower bound could have been like pi over 4, and then sine of pi over 4 would have been like root 2 over 2. Obviously, root 2 over 2 is different than pi over 4, right? But they're both constants. So even if this thing down here, this sign, it wasn't assigned 0, it was any other number. It could be a billion, it could be negative a trillion googolplex. I don't care what it is. If you take the derivative of a constant, that's always 0. Okay? Derivative of a constant, right? This is going to be always 0. Always. Always. My husband hates it when people put Z's on the ends of things in their advertising or something. Always 0. The derivative of a function, so the dx of a constant is always 0, okay? There's kind of a lot going on here, but thought bubble, right? So this whole thing here equals cosine x. Okay, now all that work and thought. Now let's compare. Our f prime of x is equal to cosine x. Well, what did we start with? We started with accumulation function where the integrand was cosine, sure, not of x, but of t. So we did all that to get from essentially a cosine of variable to a cosine variable. That's literally what the second FTC is. Is showing that the derivative of an accumulation function is the original function. That essentially taking the derivative of an accumulation function that like cancels itself out. Those are like inverse functions essentially. As long as there's going to be some nuances for when this is not just an x, if that's like an x squared or a 2x or a cosine x or something crazy, there's going to be a little nuance there. It's not too hard. And as long as the bottom number is a constant. If the bottom number is not a constant, it could get a little weirder. I don't know. It's possible that the AP could ask that. I'm not going to ask you one where the bottom's not constant. Okay, so let's go ahead and do the big reveal. Right. Second FTC. Hopefully now you're coming into this formula with a lot more understanding than you would be if I just plopped it down in front of you. So second FTC. And just like the first FTC, the kind of like caveat thing in the beginning is not that important because it's not an existence theorem, meaning it's not just saying, oh, such and such condition must exist. It's saying, hey, here's an important formula, use it. It says if f is continuous on an open interval I containing a, then for every x in the interval, I'm just going to say if f is continuous. Well, that's enough. And even that, honestly, I don't even remember myself because it's usually totally a moot point. And you don't really have to like state that before using the theorem or whatever. If f is continuous, this is true. dx of integral. And the lower bound does not have to be 0. So the accumulation functions we've been using so far start at x equals 0. You can start anywhere. Again, the reason you can do that is there's just a lot of stuff going on here. Whatever, I'll use a highlighter. If this was a different number besides 0, then that all that means is that this input value would be a different number besides 0, but still any function of a constant number is going to be a constant. And then the derivative of a constant is always going to be 0. So even if that bottom number is not 0, it doesn't matter. The end result is going to be the same, that it actually does not matter at all what the lower bound is because that's going to be a fixed value. Take the derivative of fixed value, that's going to just like go away to 0, right? That's why this thing goes away to 0, and then you end up just having that at the end. Okay, so this lower bound is, they call it A. This is any constant, so this is just a constant. The top is x. We're going to talk about later what to do if it's like a function of x, like 3x squared or cosine x or something crazy. It's not too bad. And then of the function. Now again, this does need to be, it doesn't technically have to be t, just use t, play the game. Don't use x here though. So don't, like, let's see. All right. Must use a dummy variable, not x here. Okay. So that is important. Nah, I don't get as miffed about that as some other things, but it's technically incorrect if you use an x there. Is equal to, right? So what's this whole thing mean? Again, this is going to mean the derivative of the accumulation of a function f is just equal to itself. So this is all equal to f of x. And yes, this is, that last thing is an x. It's not a t, right? So this is x, not t, right? So essentially, and again, this is really important. If you, I'm wanting to use my hand to cover it up, but you can't see my hand. It's really important. This has to have the derivative in front of it. If you're not taking the derivative of an accumulation function, if you just have an accumulation function, right, then they're probably asking you questions like we did like way back here. This would be really useful to teach with. You can go back. Asking you questions like they did back here when you're just, right, if you're not having the derivative of an accumulation function, if you're just plugging in upper bounds of an accumulation function, you're literally just finding the area under a curve. And it doesn't cancel out, right? Like, so for example, when you look at this thing here, right, g of x is not equal to f of x. Nope, not at all, right? G of x is the accumulation function of f of x. Now the derivative, if you took the derivative of both sides here, now this is where, I don't want to get too far ahead, but now applying the second FTC, right, if I took the derivative of both sides, second FTC, if I took the derivative of both sides, if I did dx of g of x equals dx of 0x f of t dt. Well, what does this right side look like? What does that look like? That right side looks just like this thing down here. It looks just like this. What is that equal to? F of x. Right? The derivative part, right? This derivative of the accumulation function, right? That cancels out. Okay? So it's this and this. That cancels out. I'm kind of putting in quotation marks, I guess a little bit, but it's like it cancels out, right? And the ddx of g of x is just g prime. So now the big kind of secret of 84, which not knowing the second FTC, you couldn't really directly use this information, but this is the kind of information that you're going to be using from now on, now you know the second FTC. This is why for the part D, I was like, we're just going to skip it, because once you know the second FTC, you kind of know all the secrets and you can just use information from before, because this is saying, oh, let me do, so this is g prime of x on the left side. On the right side, the derivative and the accumulation function cancel out. This just becomes, now not f of t, remember it becomes f of x. So this is f of x. So this says f is the derivative of g. F is the derivative of g. What? So that means all the questions that we answered in 84, f is the derivative of g. If that's true, then we could have answered these questions like, without even thinking as hard as we did, right? If f is positive, then, and f is the derivative of g, if the derivative of g is positive, g is increasing. Duh, of course it is. If the derivative of g is negative, then g is decreasing. Duh, of course it is, right? There's a relative maximum on minimum on g because f changes from negative to positive, because the derivative of g changes from negative to positive. Huh, that's what we already know. So, which also means, should I add that here? Let me see where I should add that. So I'm going to just come out here. I don't know. Going off script. So far we've had like f, let's see. Yeah, so we've had like f of x, and we took the derivative dx of that, and we got f prime of x, right? And then we took the dx of that, and we got f double prime of x. And you could keep going. But now, dun dun dun, we're going back a step, and we've now just discovered what is back a level, right? What if you go backwards, right? F double prime to F single prime, right? And now this is kind of starting to hopefully tie into 5.1. You're taking antiderivative, you're solving diffuse, taking antiderivative, so you're going backwards, you're not taking the derivative, and right, taking the derivative is going down in this chain, taking the antiderivative is going back up. So you go, right, antiderivative f double prime more or less is f prime, antiderivative f prime more or less is f, antiderivative f, boom, is, right, now we know what goes here. Now you would normally probably, without having seen this, be like, oh, I guess the integral of f. But then it's like, well, what kind of integral of f? Well, really, it's going to be this accumulation function. It doesn't have to be 0. I'm just going to put an a there. All right, so I'm going to put, and then technically this is an accumulation function. Again, you got to use the t thing. I know it's annoying, right? But this is saying if you take the ddx of this, of the accumulation function, you get f of x. So these are all now like 4 levels of derivatives, right? So that's pretty important. And understanding where this accumulation idea fits in with these other, the function f, f prime, f double prime, then you go backwards from f and you get the accumulation function, right? So that's where we had over here, if g is the accumulation function of f, so that means like in this, hello, right? Like in this problem, they said that this was equal to g of x in our problem. That means g was like down a level from f. It's like we're going into the basement, right? So that means f was actually the derivative of g, right? So like in this case, it was like f was the derivative of g. And then f prime was like the second derivative of g. I'm getting a little bit ahead of myself, but you can see how they love exploiting this. This is kind of like the heart of calculus. least Calculus 1, and how they love making sure you understand and can move between these different levels of derivatives, go forward, go backwards. Okay. Now let's do some concrete examples, and then we need to do the slight complication case for the second FTC. And then I think I'll probably just make the net change theorem thing in a different video. Let me back to where we were. Let's do some more concrete examples. We kind of tied it into the earlier stuff, so we've kind of already done it, but so as an example, okay, well, I'm just going to do example 7. Why not? Top of page 326. So for example, if they want you to find, let's see, now they can either phrase it as ddx of the accumulation function, or they can say, like on your homework, I think it says like find derivative of, and then usually, and they don't have to do this because it doesn't matter what you name it, they're usually going to name their functions capital F of x. Again, technically, that doesn't guarantee that that means it's an antiderivative. It's just kind of by convention. So like find the derivative of, and then they'll say, like in this case, like f of, oh, yeah, and in your homework, oh yeah, okay, so f of x, and then, so they're gonna do, and it doesn't have to be 0. I'm gonna do one that doesn't have 0. It literally changes nothing. -5, I don't know, x, and then let's say, we'll just use the example, it doesn't really matter. T squared plus 1 dt. All right. So don't get freaked out by this. Look, I'm telling you, there's going to be a second FTC problem on this. Again, I forget if it's a test or a quiz coming up. It's in your calendar. There's going to be a problem that's pretty much just like this, or, similar, maybe probably more similar to the next example because it's a tiny bit more complicated. People every year, like, there are so many, I feel like at least half the class ends up not just getting it wrong, but I can tell from their work on their paper that they like freak out and they're like floundering and they're like trying all this crazy stuff. This should be like the easiest question, especially a question like this if you just have x. So like for example, up here, what you really did when you saw that there's a derivative, you're taking the derivative of an accumulation function, right? If those two pieces are there, right, and the bottom of this accumulation function is a constant, if the top is just a plain old x, literally all you do is you take this x and you just replace the dummy t, and then boom, so that there's an x there instead of a t. And then it's like the ddx cancels the whole accumulation idea, and it's just f of x. So literally, when you look at this problem, again, they're saying find the derivative of this thing. If they didn't say find the derivative, you just got an accumulation function on your hands. You ain't got nothing, right? Because this f of x does not equal root x squared plus 1. No, capital F of x does not equal that. It only equals that when you take the derivative of it, okay? But you're taking the derivative here. They tell you to take the derivative. So all you're doing here is literally taking this x and plugging it in for t, right? When it's just x, you just plug in x for t, okay? So if, well, I'm not going to write that down because again, I mean, you only do it when you take the derivative. Just, it would take too many words to make sure I have enough caveats that you don't just glance at your notes one day and then misinterpret. But so the derivative of this thing, right? So f prime of x, right? You can write it out like this. You don't even technically have to do that, I guess. Negative 5x t squared plus 1 dt. Okay, right? I mean, that's essentially just what the question's asking you to do, right? So literally all you do is you take that x and you plug it in for that t. And then everything else cancels out. And so all you're left with is the square root of x squared plus 1. And you're done. That's it. You don't need to. Now, in the example that I showed up here, I kind of derived why it's true, right? Up here, I derived why it's true that when you start with an accumulation function of cosine t and you take the derivative of it, why you end up with, why you can just justify that. Why do you end up with the same thing? I derived it and said, okay, yeah, well, yeah, sure. For the accumulation function, you can take the antiderivative, which is sine. You can plug in the upper bound, plug in the lower bound, and you can manually take the derivative of those things. Oh, and that's a constant that goes away. You could work the problem that way every time. You don't need to work the problem that way every time. In fact, in this case, if you try to take the antiderivative of this thing, you're over your head. To be honest, I don't know how to take the antiderivative of that. You would need like a t outside that square root thing. We haven't even learned u substitution. You don't even know how to take that antiderivative yet. You don't need to. You do not need to. Even if it was something easy that you could take the antiderivative of, then you could work it the long way, but why? Why do that to yourself? Okay? You see the derivative of an accumulation function, you plug in the x for the t, and you're done. If this is just an x, now we're about to do one. What if it's not just an x? Okay? Hopefully that was enough to convince you to not make this harder than it has to be. Okay. Next, I'm doing example 8. This is whatever. Example 8. I'm just going to do this so visually we can split it off. Okay, example 8. And this is, find the derivative of capital F of x equals this thing. And again, this bottom thing, they just try to make it look fancy to confuse you. Literally don't care what that bottom, if it's a constant, then it's going away. Okay, again, the t's here, notice them. Again, you're taking the derivative of an accumulation function. Hold on, let me make sure you can see this 3 still. Okay, derivative of an accumulation function. Boom. More or less, it's going to cancel out. So more or less, again, you pretty much, with an asterisk, can just plug in this top bound that has your x in for this t. You actually, even if your x was in the lower bound, you could also do the same thing. Anyways, it might be a little bit weird with a negative thing, but I don't think you're going to see that. At least nothing I give you directly. Okay, so you plug in the x cubed when you take the derivative. Again, not just for this f of x thing. But there's a little bit of a trick. That's not the full answer. Okay, so let's do this. So f prime of x equals. So the first part is that, yes, it's just the cosine. And again, notice, same thing as up here. I did not, look, this is the same thing as this. Look, I didn't change it. I didn't take a derivative. I didn't take an antiderivative. I just copied it because the other stuff around it cancels out. You just keep this integrand. Okay. Cosine instead of cosine of t, cosine of x cubed. So if it's x cubed instead of x, you got to put x cubed. Okay. But now I'm not done, unfortunately. It's not super hard, but I am not quite done. Times. I'm not done. Right. So remember this little thing called chain rule. Chain rule. When did we use chain rule? Okay. Chain rule review. Um, let's say if I had, I'm going to choose something else because I don't want it to be, I don't want to confuse you with it not being exactly the same thing. So let's say if I did ddx of tangent of 2x to the fifth. 2x to the fifth. Okay. And this is back in derivatives. Okay. Again, we have like this is like our inside function. Sometimes we call it the inside function u. If you remember that, like the formulas in the front of your book are u. I alluded back in the day, to the fact that we're going to use something called u substitution integrals, which we will in a video coming up. So this is the inside function. Okay, so when we did chain rule, we did the derivative of the outside with respect to the inside first. So derivative of tan blop is secant squared blop. 2x to the fifth. Right? Again, that squared is only because of the derivative of tan is secant squared. But then we did times, right? That whole thing, I'm just going to put brackets here just to make it crystal clear. Times the derivative, the inside, right? Times the derivative of 2x to the fifth. Whatever that is. Whatever. X to, well, I gotta actually write it in there. That's a 5 there. So this would be the derivative of 2x to the fifth would be, 10x to the fourth. So 10x to the fourth, right? This thing here times secant squared. This is kind of a nasty, strange thing, but it is what it is, right? Remember that when we did chain rule? Okay. Well, even though this is so closely related to integrals and kind of our focus in chapter 5 is integrals, notice what we're actually doing here, right? We're actually taking a derivative. Okay. So we took a derivative of this thing when we normally would have just an x here. Just like when we took the derivative of this thing, we would normally just have an x here. So that means our first step, like our derivative outside with respect to the inside, was just doing what we normally would do. We would normally, like I said with this green little arrow thing, we would normally just plug in whatever's there in for that input and call it a day. But normally the thing we plugged in is just an x. Just like for this tan thing down here, we normally say derivative tan x, secant squared x, done. But if that inside function was not just x, but another function of x, we got to multiply at the end by the derivative of the derivative of the inside. So in this case, we have to multiply by the dx of x cubed. Normally you would just go ahead and write out the answer, but I'm just being very explicit. So the derivative of x cubed is 3x squared, and then times cosine of x cubed. And notice the x cubed stays there, right? X cubed stays inside the cosine as is. Okay, so in terms of a direct application of the second FTC, that's as hard as it gets, is where your upper bound or your x type bound is not just x, but is some other function of x. And you have to not just plug that in for where this t is and say, yeah, derivative accumulation function cancel. You just plug it in, but you also have to multiply by the derivative of the inside if the inside is not just x. Okay, so we can do one final thing, and then I can cut off this colossal video and oh, you're gonna judge me, but at almost 2 a.m. I can go eat dinner. Yep. Oh, okay. So let's do an example. Another example. All right, I'm gonna do example 103 because why not? All right. So this is page 331, number 103. Okay. So use the second fundamental theorem of calculus to find f prime of x. So they want to find f prime of x if f of x equals and okay, they have a 0 there, but again, just keep in mind it doesn't matter that it's a 0. X, is that a 3? All right, sure. Well, all right, whatever. I'm just going to go along with exactly what the function says. It happens to also be x cubed. Hopefully you can extrapolate in your mind. Now this one's a tiny bit more confusing because they do have a t squared in here already. All right. So I'm going to go fairly fast with this. So no, it needs to be the capital one. So f prime of x can equal the d dx of this thing sine. What am I writing? Brain fart. Nope, now I'm writing with an eraser. I'm getting delusional. Okay, so again, what I'm going to basically do is plug this in for t, not for t squared, for t. I still got to square it. And then I'm going to have to multiply, use chain rule, right? Then I'm going to need chain rule. Okay, because this thing is x cubed, not just x. Okay, so this is going to be sine of x cubed squared. So I am going to go ahead and simplify that. Hopefully you remember that you multiply exponents raised to other exponents times the derivative. And again, you can just write the derivative. You don't have to write it out like this, but I'm just doing it because. So this, I'm just going to write this in the front. It just looks better. So the derivative of x cubed is 3x squared times the sine of x to the 6th. That's it. Okay, I'm cutting this video off. It's almost an hour and a half long. I will be back. Another video fairly briefly explaining the net. What's called the net change theorem. I'm also going to tell you it's not really a theorem. It's kind of a far reach calling it a theorem. Okay, hope you understood all this. All right, goodbye. Godspeed.